Swayam Prabha. Digital India. Educated India.
In our earlier lecture, you have seen how we can calculate the thermal stresses in a rectangular plate with symmetric and asymmetric distribution of temperature in the height direction. You will find that there are many applications wherein you are going to have cylinder or cylindrical vessels which will consist of some fluid at elevated temperature or at sub-zero temperature, as a result of which there will be variation of temperature in the radial direction. We have already come across the problems of heat exchangers where the temperature distribution in the radial direction is well known logarithmic distribution. We would like to look into how the temperature distribution in the radial direction will give rise to thermal stresses. We would like to consider therefore problem to be thermal stresses in hollow disc or cylinder. You could have a situation of this type or a situation like this. There is a pressure vessel or a cylindrical vessel which is going to have temperature variation in the radial direction like this, and we would like to calculate the stresses. If we calculate the stresses for a situation like this, where there is internal radius and external radius, if you are interested in finding out the stresses for internal radius equal to 0, that will give you the solution for thick disc or thick cylinder. So, therefore, or rather solid cylinder and solid disc. So, therefore, we would like to consider the case of hollow disc and hollow cylinder. And as we have seen earlier, that when you have the case of hollow disc like this, then you can have a situation conforming to plane stress, but when you are going to have a cylindrical vessel like this, you are going to have a condition which will conform more to the plane strain condition. We will be more concerned about this case. I would like you to think about that if we have a temperature variation in the radial direction like this, let us say that there is high temperature at the inner wall and low temperature at the outer wall. So, what I mean is this, that we have Ta greater than Tb. I would like you to think for a while what will be the stress state, what do you expect to happen to the stress at the inner wall and at the same time stress at the outer wall. So, you have high temperature at the inner wall. So, therefore, all the circles which are closer to A, they will try to expand more than the circles which are at the outer edges, and therefore, you are going to have a situation which will give rise to compressive stresses here and tensile stresses there. So, we would like to look into the whether we really get that stress distribution as we expect. As I have said that we will like to consider the case of long cylinder, they will have a stress state which conforms to more with the plane strain condition, and for the plane strain condition we can write the stress strain relationship, stress strain temperature relationship as given here. You have stress sigma r, sigma theta, and shear stress tau r theta is given by E by 1 minus 2 nu into 1 plus nu into the matrix which is there, which is the Poisson's ratio matrix, and then we have the strains epsilon r minus 1 plus nu into alpha t, so also epsilon theta minus 1 plus nu into alpha t and gamma r theta. So, herein E is the modulus of elasticity and nu is Poisson's ratio, and at the same time we are going to have the stress in the axial direction which is related to sigma r and sigma theta. So, this sigma z is equal to nu times sigma r plus sigma theta. For the cylindrical problems or even for the problem of thick cylinder, we derive the relationship, the equilibrium equation. The equilibrium equation for this problem also will be similar, and therefore, the governing equation for the stress distribution is given by d sigma r dr plus sigma r minus sigma theta divided by r equal to 0. So, that is the governing equation of distribution of radial stress and tangential stress. Let us consider this equation to be number 1. Now, from the stress strain relationship that we had shown you earlier, we can write the stresses, and the stresses are going to be given by we will have this sigma r is equal to this constant E by 1 minus 2 nu into 1 plus nu, and then we are going to have 1 minus nu epsilon r plus nu times epsilon theta, then we are going to have one minus nu into 1 plus nu alpha theta minus nu into 1 plus nu alpha t, I am sorry, this is alpha t. So, this gives us, if we represent this constant as, let us say, C bar, then we have 1 minus nu epsilon r plus nu times epsilon theta, and then if we take common here, you can see that we will have this nu cancelling out. So, we will be left with 1 plus nu into alpha t. So, that is the expression for sigma theta, and I am sorry, that is the expression for sigma r. Similarly, we can derive the expression for sigma theta. It is going to be C bar 1 minus nu times epsilon theta plus nu times epsilon r minus 1 plus nu alpha t. That is the expression for the stresses. And now, if we substitute these relations into the differential equation, then we are going to get, so if we substitute now d sigma r dr, noting also the fact that we can also write the expression for the strains. We have epsilon r is given by du dr, and epsilon theta is equal to u by r. It is similar to that we had done in the case of thick cylinder. So, now if I try to substitute the value into the equation of equilibrium, then we will have the constant which is C bar c bar into, we will differentiate this 1 minus nu d2u dr square, then we are going to get nu times u theta. So, therefore, we will have it nu times u by r, and then we are left, we are also having the expression for this is, we are also going to have this 1 plus nu So, d sigma dr, it will give us the derivative of this. So, we will have derivative of this. So, therefore, 1 plus nu alpha dt dr. So, we will have then minus nu u by r square, then the other terms 1 by r into 1 minus nu du dr plus nu u by r minus 1 minus nu into u by r minus nu du dr, this is whole thing equal to 0. So, if you try to cancel some of the terms here, you will see that this term is going to cancel with this one, and then we are going to have this term cancelling with this term. So, rest of the terms will be remaining, and when we try to simplify them, it becomes 1 minus nu d2u dr square plus 1 by r du dr minus nu by r du dr minus 1 minus nu u by r square equal to 1 plus nu into alpha dt dr, and these two terms can be combined to give us again 1 minus nu into du dr by r. So, therefore, finally, we can write this equation in the following form: d2u dr square plus 1 by r du dr minus u by r square is equal to 1 plus nu by 1 minus nu alpha dt dr, and this is the expression on the left hand side which you have already come across in connection with thick cylinder, and this expression can be written here like this: d dr 1 by r d ur dr sorry 1 plus nu by 1 minus nu alpha dt dr. So, that is the final expression for the displacement that is going to come about in the temperature field, and we can integrate this relationship very easily, and finally, we are going to get u in the form u equal to C1r plus C2 by r plus 1 plus nu 1 minus nu alpha 1 by r integration dr dr. And since the cylinder is prolonged between the domain r equal to a to r equal to b, this is going to be, this will really have, if you are interested in finding out the displacement at a point, let us say radial distance r from the center, then this integration should be a to r. Now, after having got this displacement, we can get our strains u theta, which is nothing but u by r, is equal to C1 plus C2 by r square 1 plus nu by 1 minus nu alpha by r square integral Tr dr. Similarly, epsilon r, which is given by du dr, so it is going to be equal to C1 minus C2 by r square minus 1 plus nu by 1 minus nu alpha by r square integration Tr dr, and when you integrate, when you differentiate this expression, you get another term 1 plus nu 1 minus nu alpha t. Here what I mean is that our epsilon r is nothing but du dr. So, when we try to differentiate this expression, we have two terms, one is 1 by r, other one is integral Tr dr. So, when we differentiate this, it gives us a term equal to alpha by r square, and when we differentiate this integral, we get Tr, that r cancels with r. So, therefore, we will be left with alpha t. So, these are the strains, and once we substitute the strains in the expression for the stress, we get the stresses as follows, particularly sigma r is equal to, we can again write, we have the constant C bar 1 minus nu epsilon r plus nu times epsilon theta 1 plus nu alpha t, noting that we have epsilon r is equal to du dr and u is shown there. We can now write that this expression, it is nothing but C bar into 1 minus nu C1 minus 1 minus nu C2 by r square minus 1 plus nu alpha by r square Tr dr, and then we also have the differentiation of this term will give us 1 plus nu into alpha t, then we have nu times epsilon theta, which will give us, epsilon theta is u by r. So, therefore, it will give us nu times C1 plus nu times C2 by r square plus nu times 1 plus nu by 1 minus nu alpha by r square Tr dr. And also we are going to have one more term, which is one plus nu into alpha t minus 1 plus nu into alpha t. So, therefore, you see that this term gets cancelled with this one. Finally, we are going to get the expression for sigma r. Sigma is going to involve the constants like C1 and C2. As in the case of thick cylinder, we solve for these constants by looking into the boundary condition. Here also we have to look into the boundary condition and solve for the constants. So, let us try to consider what is going to be the boundary condition in the problem of this type of cylinder. So, if you consider now this typical cylinder here, just the cross section of it, you have the radial stress. There is no external loading acting on the inner wall, and therefore, the radial stress on this boundary is going to be 0. Similarly, there is no external loading on the outer boundary. So, therefore, the radial stress on the outer boundary too is 0. So, therefore, we can now consider that both the surfaces are free of any radial stress, therefore, sigma r equal to 0. Now, let us see how do we get the value of the radial stress at the inner radius and outer radius. So, we have the expression for the stress, radial stress, which is we have written here that C bar into 1 minus nu into C1 minus 1 minus nu C2 by r square minus 1 plus nu alpha by r square. So, if we now try to consider that this sigma r, we will try to consider the case that sigma r at the inner radius. So, therefore, sigma r for r equal to a, and that is 0, and therefore, now if I see here, we are going to get now we can take the value of this C bar. So, if we take the value of this C bar inside, C bar is nothing but 1 minus 2 nu into 1 plus nu. So, therefore, we can now write here we have certain terms here. We can consider now it is C1 in, we will have one term cancelling here. So, therefore, we can write now, if we write in terms of the modulus of elasticity and Poisson's ratio, then this is going to be nu, and then we have only C1 divided by 1 minus 2 nu, and then C2 we have here, it is nothing but 1 minus 2 nu C2 by r square. So, therefore, if we now cancel 1 minus 2 nu, we are going to get C2 by, and r is equal to a. So, therefore, it is a square. So, that is the expression for the first term. And now, coming to this part, here in our limits of the integration is a to a. So, therefore, this quantity will get knocked out, there is no contribution. Similarly, here this integral is going to be having the limits a to a. So, therefore, this is not going to give rise to any contribution. Finally, we find that sigma r equal to 0, which is nothing but E by 1 plus nu into C1 by 1 minus 2 nu minus C2 by a square. I want to again to note that we have made use of the fact that this C1 bar, which is nothing but E by 1 minus 2 nu into 1 plus nu. So, that substitution has been made in the expression for the stress sigma r, and that is how we get this expression. Similarly, if you are trying to now consider the calculation of sigma r at the point r equal to b, what it will mean is that we have to substitute r equal to b here, and so also r equal to b here, and the limits of integration would be a to b in both the cases. So, if we now do that, we find sigma r is equal to sigma r at r equal to b, which is 0, and this would again give rise to E by 1 plus nu C1 by 1 minus 2 nu minus C2 by b square minus, we will have some simplification possible from these two terms, and that will finally give us E into alpha 1 minus nu b square, and this is a to b tr dr. So, this is what is going to be the expression for the stresses at sigma r, stresses sigma r at r equal to a and r equal to b, and therefore, now you have got two expressions to solve for the two constants C1 and C2, and obviously we find from the first relationship that C2 is equal to C1 a square divided by 1 minus 2 nu. Similarly, if we now consider this C1, so from this relationship we will get C1 is equal to 1 plus nu into 1 minus 2 nu divided by 1 minus nu, and this is 1 into alpha by b square minus a square a to b tr dr. So, that is the constant C2, and that is the constant C1, and therefore, C2 is equal to 1 plus nu 1 minus nu a square alpha divided by b square minus a square a to b tr dr. So, we have got the two constants along the lines we had taken for the thick cylinder with internal pressure, and now after getting these two constants we again get back to the relationship for sigma r which we had obtained earlier, and once we make this substitution we will get the value of the stresses. So, these stresses are now going to be so this sigma r is finally going to be given by this expression. So, just I will take the final value. So, herein sigma r given by E alpha by 1 minus nu 1 by r square into r square minus a square by b square minus a square a to b tr dr minus a to r tr dr. So, that is the expression for sigma r, and we have already got the expression for sigma theta, and we can finally substitute the value for the displacement, and we get the expression for the sigma theta as E into alpha by 1 minus nu into 1 by r square into r square plus a square by b square minus a square a to b tr dr plus a to r tr dr minus tr square. So, that is the stress in the circumferential direction, and when we try to take the product nu times sigma r plus sigma theta, it gives us the value that it is E alpha by 1 minus nu 2 by b square minus a square a to b tr dr minus t. So, that is the stress in the axial direction, and you must not forget that this stress distribution corresponds to plane strain. So, if you are interested in finding out the stress distribution corresponding to plane stress, you can as well go in for the steps that we have given here, and the difference would be that this relationship between the stress and strain is going to be different, but all the steps are going to be remaining the same. Now, let us consider the application of this formula. Let us consider that we have the well known case of thermal, when heat exchangers are conducting or exchanging heat, you find that the wall temperature is going to vary from the inner wall to the outer wall, and this, if we plot in this direction temperature and in this direction radius, then it is going to be like this. So, we have the vessel of radius, again r equal to A to r equal to B, and most often the temperature variation is going to be, if we take this as the datum, this Tb temperature as the datum, then in that case the temperature variation is going to be logarithmic, and it is given by Ta into ln B by R divided by ln B by A. Now, we need we have to substitute this temperature distribution in the expression for stresses. So, if we now consider the radial stress, that radial stress is going to be of this form: E alpha 1 minus nu 1 by r square minus a square by b square minus a square a to b Tr dr minus a to r Tr dr. So, we are going to have this form, and now if we substitute the value for the temperature, so we again have the expression here sigma r E alpha 1 minus nu 1 by r square minus a square by b square minus a square a to b Tr dr minus a to r Tr dr. So, that is the sigma r stress. So, we will now solve for the temperature distribution given by Ta ln B by R divided by ln B by A. So, we can now write sigma r E alpha 1 minus nu 1 by r square minus r square minus a square divided by b square minus a square, and we have this thing as a to b Ta ln B by R ln B by A, and we have R dr. Second term A to R Ta ln B by R divided by ln b by a r dr. We have the integration of the term ln b by r into r dr. So, therefore, let us look into the integration of this term. Integration of r ln b by r. So, we have product of two functions r and ln b by r. So, if we consider this is the first function, this is the second function, then we will consider the integration of the first function r, and therefore, it will give us r square by 2 ln b by r minus integration of the first function, that is r square by 2, differentiation of this function will give us 1 by b by r. So, that will be r by b, and differentiation of b by r will give us minus b by r square dr. So, that is the expression which we get, and this has got to be integrated. And now, if we rewrite, this is r square by 2 ln b by r plus, this is now we are going to get cancellation, it is simply going to be r by 2, and therefore, we will have this thing, this minus will cancel, it will give us plus. So, therefore, it is 1 by 2 r square by 2, and finally, this gives us r square by 2 ln b by r plus r square by 4. So, that is the expression for the integral, and therefore, if we now substitute the value here, you see that limits of integrations are a to b. So, we will have two terms coming for each of them, and therefore, sigma r is equal to E alpha 1 minus nu 1 by r square minus a square b square minus a square, then we have T a by ln b by a common multiplier, and now these terms have to be between the limits a to b. So, we can now write, that will give us so for the limits b it will be 0. So, therefore, we will be simply having a square by 2. For limit r equal to b, it will be b square by 2 ln b by b, which is 0. So, therefore, it is minus a square ln b by a. So, that gives us the terms for a and b, and then this one will give us 1 by 4 b square minus a square. So, that is the term that we get considering the first term of the expression for sigma r, and the second term will give us T a by ln b by a, and this is going to be limits a to r. So, therefore, it will be r square by 2 ln b by r minus a square by 2 ln b by a plus r square minus a square by 4. So, that is the expression for sigma r. finally there is some cancellations possible, and we can write finally sigma r to be given by E alpha T A divided by 1 minus nu ln B by A into A square by R square minus A square divided by B square minus A square ln B by A. Then we have R square minus A square divided by 2R square minus ln B by R. Then A square by R square ln B by A minus R square minus A square divided by 2R square. So, these two terms are going to cancel. Finally, we will be left with the expression there, and which is in simplified form E alpha T A by 2 into 1 minus nu ln B by A minus ln B by R minus A square by R square minus A square B square minus A square minus 1 into ln B by A. So, this is the expression of the stress sigma r. Similarly, once you do the integration involved in the expression for sigma theta and sigma z, you can find out the expression for these components as well. So, we finally get these components. We can also write the expression of this sigma r in a little different form, which is useful. So, let us write first sigma r in slightly different form. E alpha T A divided by 2 into 1 minus nu ln B by A minus ln B by R minus A square by B square minus A square into 1 minus B square by R square ln B by A. So, that is actually simply we have tried to keep these two terms together, and then we have taken the other things. Of course, we have simplified this one, and once we simplify this, it will be A square by B square minus R square by R square into B square minus A square. So, therefore, we can write like this. Similarly, if we write the expression for sigma theta in this format, sigma theta is going to be nothing but this common terms will remain the same, and then we will have the other terms 1 minus ln B by R A square by B square minus A square into 1 plus b square by r square ln b by a. So that's the expression for sigma theta, and sigma z, which is nothing but nu times sigma r plus sigma theta minus E alpha t. So if I do all that, in fact we had already got sigma z in a form which is here. Sigma z is equal to E alpha by 2 by b square minus a square a to b tr minus dr minus t. So if we do all this, then this sigma z is going to be like this, 1 minus 2 times ln b by r minus 2 times a square b square minus a square ln b by a. So these are the three components of stresses. So let me just have everything at one place. So this is the expression for sigma r, sigma theta and sigma z. Now let us try to consider the values of the stresses at the two extreme radii. What happens to these stresses? You find that this sigma r, here you will find that b is greater than r. So therefore this term is always greater than unity, and therefore it is negative, it will become positive. And then we are going to have this term b by r is always greater than unity, and therefore we might get some value which we are going to get something negative. Finally what we find is that this stress is going to have value all the time, this value is going to be negative, and the stresses sigma theta and sigma z, let us look into the position here. If r equal to a, then we will find that this stress is 1 minus ln b by a square by b square minus a square into 1 plus b square by a square ln b by a. So that will now become, it is b square plus a square by a square. So sigma theta will get that expression, and therefore we can write now at r equal to a, sigma theta is equal to E alpha T a divided by 2 into 1 minus nu ln b by a, that into 1 minus. So here we are going to get this is going to be b square by a square plus 1. So these two, again this is b by a, so these two terms can be combined together. It will finally give us 2b square by b square minus a square ln b by a. So that's the stress sigma theta. And if we now calculate the value of sigma z at b r equal to a, then also we are going to get these two terms will get combined, and it will also give me the same value. So it will be minus 2 ln b by a minus 2 a square by b square minus a square into ln b by a. So these two will again give us 2b square by b square minus a square ln b by a. So this sigma theta is equal to sigma z, and this stress at r equal to a, you will find that these two term, this particular term is going to be more than unity, and therefore we will have a negative stress. And at the same time, if you calculate the stress at the outer radii, so at outer radii it is going to be given by sigma theta is equal to again sigma z, and it is E alpha T a by 2 into 1 minus nu ln b by a into 1 minus 2 a square by B square minus A square ln B by A. So, this is the stress at the outer radii. So, these variations of the stresses, once we plot, it looks like this. We have stresses plotted in this direction, radius in this direction. You will have this as the variation of sigma theta, this is the variation of sigma z. Here in at the internal radius we have both are equal, at the external radius both are equal, and sigma r is always a compressive stress. So, this is how you are going to find the stress variation in the cylinder with temperature at the inner wall higher than the temperature at the outer wall. So, you can now see that the stresses at the outer wall is tensile and stresses at the inner wall is compressive. Let us try to see whether it is tallying with our expectations. As we started saying at the beginning, if temperature here is Ta, temperature here is Tb, if Ta is greater than Tb, then we expect the inner fibers to expand more than the outer fibers. So, their expansion will be arrested or rather constrained by this lower expansion of the outer fibers, and hence these fibers will be subjected to compressive stresses, and since these fibers are trying to extend, they will try to generate a tensile stress at the outer fiber which are not expanding to that extent. So, if you have the inner wall at a high temperature, you expect these fibers to be subjected to compression because of the smaller expansion of the outer fibers, and at the same time, since these are expanding more, they will try to induce tension in the outer fibers or fibers located at the outer radius. This is one of the reasons which you can understand that why when we pour high temperature water in a glass, it generally cracks. So, once you are trying to put water inside the glass, you are going to have higher temperature at the inner surface and the outer walls are still at room temperature or cooler temperature or lower temperature, and this is going to induce tensile stress at the outer radii, and this tensile stress, glass being a brittle material, is very dangerous and therefore it cracks. Similarly, if you try to consider that you have a glass, particularly if you think of a chimney and its glass, it is already at high temperature. If you pour a drop of water, the portion where you have dropped water, it is getting cooler, and if it is getting cooler, it is trying to contract, but the material which is outside, it is not allowing to go, it is not going to allow it to contract, and therefore tensile stresses will be generated at the location, and hence cracking will take place. So, what I said that in the case of a glass of a chimney, it is already hot, and if you pour a drop of water at the outer surface, that portion which is in contact with the water is going to be cooling down and it is trying to contract, and since the material outside is at high temperature, they cannot allow its contraction to take place, and hence tensile stresses will be generated and there will be cracking.